Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Midterm Solutions, Summer 22. As always, please be a attentive listener while watching this video. By way of introduction, the midterm accommodations are now finally complete, and in some cases this was just by fiat because we ran out of time and I couldn't make connections. But anyway, so pursuant to putting this behind us finally and providing some useful materials to help prepare for the upcoming important comprehensive final, here are the solutions. And please be aware that the rigor and testing mechanisms for the final exam will be very similar to the midterm. And although the landing strip is much shorter, so you should know that, and accommodations will be more limited because of COD administrative processes. So plan early for this and begin preparing early as well. So here were the directions. There were 12 equally weighted questions. The answers had to be entered to Blackboard for the problem to yield credit for the student. And so that instruction was important, and we discussed in class why that was important for academic integrity. There are opportunities for VTC students to upload their solutions, and brick and mortar people turned in PDFs of their work. And the standard time for this test was 110 minutes, and the clock starts when you put in the password entered by your proctor. And it will auto-submit at the end of your allotted time. And accommodations were handled by the proctors. Okay, so here we go. Question number 1 said, determine if the following series converges or diverges. If you invoke a test to demonstrate your conclusion, you must reference the requirements for the test and explain carefully why the requirements are satisfied. If the series converges and you can sum the series, stating the value of that is sufficient. Some students wanted to use tests that worked only for positive terms, and so that was a recipe not to be successful on this because some of the terms here are negative, and many of the tests we had were for positive things only. And some students wanted to do a ratio test, and you can do that, but it's sort of tricky to do that because if you're comparing this to 1 over n squared, unless you're trying to, and you can't use the limit comparison test because these are negative. And so what you had to do was argue carefully about this denominator and its relationship to n squared. The best way to do this problem was the way I did it, and here it is. This is a telescoping series. So you did a partial fraction decomposition of the expression here, and you got 1 over n minus 5 minus 1 over n minus 8. Now, there's a gap here between these, so these don't begin canceling immediately. There's a gap, and so you have to write out a few fractions, and when you add those fractions together that don't cancel, you get minus 11 over 6, which is the answer that you should have. Beyond that, the fractions will cancel one with another, and so that's the answer that would have netted full credit for this problem. The directions for the second one are very much the same, but again, you have a series that is an alternating series. We hadn't discussed the alternating series test yet, and the alternating series test can prove something converges, but it will not prove that something diverges. It's a little subtle that way, and so I didn't expect you to do that either. But what will apply here is the ratio test, which we did cover because taking the absolute values, so those signs will drop out. And so that's the way, that's I think the best way to approach this problem. So you need to compute what is the limit as n goes to infinity of an plus 1 over an, and we have to force that, if we can, to be less than 1. But when we start computing that limit, and here you do the standard thing of here you're doing the standard thing of multiplying by the reciprocal, and you do a lot of cancellation here. And so when you simplify this this down, and there's several ways, several steps to that, but the minus sign goes away, and when you're looking at this, this will end up, the ratio of n plus 2 over n plus 1 will be 1, and here that ratio is 1, so this is absolute value of 8 over 5. This is the absolute value of minus 8 over 5, which will be 8 over 5. Now, so that will never be less than 1. That's greater than 1. That means by the ratio test, the series diverges. I think that's the cleanest way to have done the problem, and in many instances, the only right way. If you just invoke the ratio test, you should show me the work that 8 over 5, in fact, is the ratio. Same directions here. This ends up being a geometric series, so the easiest thing to do is compute the value, because the value will be sufficient. So let's compute the value of this geometric series. Okay, so we start doing some algebra. Again, you should pause this if you want to. But what we're able to do is eventually, by doing algebra and rewriting the term, we can get this to be very much in the form of the geometric series. This is 144. That is 4 over 9 raised to the n minus 1. We have a formula for that. It's the first term, 1 minus r. And so we're good with that. You should simplify this, and your answer at the end of this problem should be 1296 over 5. Question 4, same kind of directions, but we have this. Now here, a number of students lost points because they were confusing the terms with the series. And so the thing to use here is the nth term divergence test. So you should have told me that the limit of the nth term is 2, as n goes to infinity. And since 2 is not equal to 0, the series diverges. And so you should have told me that that was 2, and made the argument similar to what I did. Doing it, so you should say it does not equal 0, and you should say it equals 2, does not equal 0. I didn't write it that way, but you should have. And so the limit of the series of the terms is 2, but since that doesn't equal 0, you know the series diverges by the nth term divergence test. Again, the same directions for question number 5, but now we have n e to the minus n squared. Now, there was a lot of things that you really would have to show if you wanted to try to do a ratio test. You could do a ratio test with this, but that's not really what I was looking for. I was looking for you to do, and you would have to argue about, you know, what these coefficients are, and what is the limit as this goes to infinity, and talk through that. That could have been one path, but that wasn't the path I really was expecting you to do with this. The integral test. Now, the thing is a little bit interesting, because even though it's decreasing beyond this point, the integral test, applying it directly, you would have computed the integral from 1 up to this point, and you can solve for what this point is. This point is the square root of 2 over 2. And so you'd have to integrate that, and of course you get a finite number. There's a finite area there, but then beyond that, the derivative is decreasing. Now, you have to show that it's decreasing to apply that. So you'd be taking the derivative of this. That involves the product rule, and you factor out a common thing. So you see, it only is decreasing after this is equal to 0, which is where you get the square root of 2 over 2. So this is decreasing, it is positive, so you can use the integral test. And the integral test, we had to compute this so it's going to be the sum of this one and this one is what you should have had. So the integral converges, but the series, all you can say is the series converges. And some students said, oh, the series converges to the same value. It doesn't necessarily, and in this case, it doesn't either. So that was this problem. Now in question 6, now we're getting, I think, away from series and sequence problems, which I guess is perhaps good. This is some other stuff. So we're to evaluate the following integral or prove it diverges. Many students just said it diverges and didn't say anything more. That, of course, is not right because it will converge. And here is a solution. Okay, so one thing is you're taking for an improper integral, this is limit as b goes to infinity of that. So now you have to be dealing with this. And the best way to do this, I think, and we did a problem like this in class, is we're going to do a substitution. We're going to note that this denominator is e to the x whole squared plus root 3 whole squared. And so when we make that substitution, this is motivating by a Trig substitution. Let's see, e to the x is equal to square root of 3 tan theta. So that means tan theta is, there's theta, and so tangent is opposite over hypotenuse, or excuse me, opposite over adjacent. So that is e to the x over square root of 3. That means this is the square root of e to the 2x plus 3, which is that denominator. And then you figure out what is dx, and you also then look at your limits and see what happens with your limits. So as x goes from 0 to b, and b is infinity, you can argue that the tangent theta is going from 1 over square root of 3 to infinity, and then theta is going from pi over 6 to pi over 2. Okay, so we changed the variables then, so we get, this is going to be the integral from pi over 6 to pi over 2. E to the x, dx, is going to be square root of 3 secant squared theta, and that should say d theta there. That's a typo that I didn't do right. So that is d theta. So there's what I get for dx, and the denominator becomes 3 tangent squared plus 1. But the tangent squared theta plus 1 is a secant squared theta, so those cancel out, and I get root 3 over 3, which I can pull out, and then I have a constant times the length of this interval, which is pi over 3. And so the final answer is this. And that square root of 3 could be written other ways, like this. And I counted all of those correct. But that's what you should have done with this problem, so it converges, and that's the value of the integral. Question 7, you were to determine the area of the region bounded by x equal y squared plus 1, x equal 5, y equal minus 3, and y equal 3. Well, drawing the region is key, and so the regions that you're really talking about, whenever you put all those together, there are 3 distinct regions. There will be 3 distinct integrals, and whenever I think about the easiest way to compute this, you could do other things, but it's much more complicated. You really should be drawing your slice this way and integrating dy. Okay, so when we start down here, we'll go from minus 3 to minus 2. And the one that's on top is the y squared plus 1, and the one that's on bottom is 5. And so you're integrating that using the Washer method. And so, or excuse me, not Washer method. This isn't a volume. This is an area. So you just take the difference between those two. The one on top minus the one on bottom, and you will calculate that. But now from minus 2 to 2, on top is 5, and on bottom is y squared plus 1, so it's this way. And again, it is important that you did minus the whole of y squared plus 1, and so you'll be computing that. And then up here, you're going from 2 to 3, and you're doing, on top is y squared plus 1, the red curve, and on bottom again is the 5. So you have to compute these 3 integrals, and again, you can pause the video to do that. But these are pretty straightforward across the board, and you get those, plug in all the numbers, and you get 46 over 3. Question 8, you were to evaluate the following integral, and this is like an example we did in class as well. This is integration by parts. And so we'll integrate this by, and here we go with that. So we're going to let u equal the arctangent of 1 over x. dv is x. So dv is dx. So when we integrate, v is going to be x. And here, when you take the derivative, it's going to be 1 over 1 plus 1 over x whole squared. But then I have to use the chain rule on this. And so when I use the chain rule, I get minus 1 over x squared. Now, it turns out that that simplifies really nicely if you do the algebra. So du really is minus 1 over x squared plus 1 dx. So then you're going to do uv minus the integral of v du, uv minus the integral of v du, and you'll get a minus here, so that makes that into a plus. You're just plugging numbers in here. So when you put 1 in, you will have minus pi over 4 for this. When you put square root of 3 in, you will get square root of 3 times pi over 6. And then you will go here, and this is just u equal x squared plus 1, and you have to mess around with the constant, but you get 1/2 ln of x squared plus 1, and there's different ways you could write it. This is how I wrote the answer simplified. I could have got a common denominator there, but I checked what number that you had and see if you got the right answer. Here's another way to have written the answer in a simplified in a different form, getting a common denominator up here, and I did check, to see what you had before I gave you credit. So that was this problem. Now here, you were supposed to find the exact length of this curve. X is equal to 1/3 square root of y times the whole of y minus 3, as y goes from 1 to 9, and so you had to remember the arc length formula and apply it here. Okay, so here's what x was. I'm again using the calculus notations to make the derivatives easier to calculate. And the thing that's easiest to do here is to use the form where we're having dy on the outside. And so you need dx dy. And if I take that derivative, I will get this. Notice that this is negative here. And then, of course, I'm going to square that because I want to take 1 plus that business squared. So I am going to square it. I get this. But again, as we saw in the examples in class, a problem like this, if you add 1, you're really just changing that minus 1/2 to a plus 1/2, and you have a perfect square as this, which will be nice to take the square root of. So the arc length then is going to be the square root of 1 plus x dx dy whole squared, and the square root of that. And so when you take the square root, and for these ranges it's positive, so you simply can, the square root of this thing squared is just that. And so this is a pretty simple integral to evaluate. Again, remember that was a negative 1/2, so if you evaluate that, you get 32 over 3. Question 11. I did not ask you to integrate this. I simply said determine the partial fraction decomposition for the following expression. And you could use Heaviside on 2 of these factors, but you had to do something else with just the x minus 1 factor by itself. And some people just wrote kind of a very general formula for this, and they didn't calculate what A, B, and C are, and that was pretty much what I was asking you to do. So anyway, let's look at the solution to this. Okay, so what you should get is 8 over x plus 6 minus 1 over x minus 1 plus 4 over x minus 1 whole squared. And again, you could use Heaviside cover-up on this one and Heaviside cover-up on this one. You had to go back to using algebra to get this. But Heaviside could save you 2/3 of the calculation. That made it worthwhile. Finally, problem 12, you find the volume of the solid revolution formed by revolving the region bounded by y equal 2x minus x squared, and the x-axis about the y-axis. So let's look at the picture. Here is the red curve that you drew, and you saw it hits at 0 and 2. That is useful information. So here's one boundary, here's the other boundary, and you're taking that around the y-axis. You could do it the other way, but that's like really hard. And so what you really should do is draw your slices this way, and then it is much simpler. And this way, if you're going around, we're taking the slice parallel to the axis of revolution. So that means that this is a shell method. And so we're going around, so this is going to be 2 pi r. R is the distance to the slice, so that is going to be x, and you're integrating dx. And then the height is going to be 2x minus x squared minus 0. And so this is the integral you have to compute. That's not too bad. Don't forget the pi, and it's 8 pi over 3. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. And remember, there's a huge upside opportunity on the final exam in this course. Take advantage of that. God bless you all, and I will see you in